Alright, hell yeah. So we have the Physics Olympiad. These are past exams. This is exam 2023, and let's get to it. So the first problem is a relative velocity problem. We're at an airport. It says amusing airport adventures. So Malachi is going to be using the travelator. You know what I mean? It's a moving escalator and a flat escalator. You know what I mean? It allows you to walk, and then it also moves so you can get to your destination faster. Cool. And so we're kind of playing around with that. Malachi is also with a group of folks, and so let's just get to it. So a group of students are walking at a speed of 1 meter per second. And they're going to walk alongside the travelator with, next to Malachi. And the travelator is moving at a speed of 0.7. So question 1 says, one of the students, so this, Malachi, is going to walk along the travelator and is going to walk in the same direction as the group. And so it asks, how fast must Malachi walk to move at the same speed as the rest of the group? So again, the group is moving at a speed of 1 meter per second. And unless I read it wrong, in this case, the travelator is moving at the same direction as the group. So, just kind of intuitively, if the group's traveling at 1 meter per second, and then let's just make up our own problem. Let's say the travelator is also moving at 1 meter per second. Well, couldn't Malachi just stand on the travelator, and then while the group has to walk? And so Malachi, in that situation, wouldn't have to walk at all. But the travelator isn't very fast. So now let's do our own problem. Let's say the travelator is just half the speed, 0.5 meters per second. The group is moving at a speed of 1 meter per second. And so the travelator only moves at half that speed. So Malachi would have to make up the other half. So Malachi would have to walk at a speed of 0.5 meters per second. So sweet. You know what I mean? And even though this is like super basic, and if you can do it, just cool, just kind of shout out the answer. But so now we're going to say the group, or how the problem is stated. The group moves at 1 meter per second. The travelator moves at 0.7 meters per second. So Malachi would have to move at a speed of 0.3 meters per second, because we see Malachi's walking speed is 0.3 plus the speed of the travelator, which is 0.7, and that's going to be the speed. That's going to be Malachi's total speed relative to the ground is 1 meter per second. But even if you're not into like the technical nature of like, well, speed relative to what, we kind of just understand that, hell yeah, you want to get to point A to point B. If you're on the travelator, you can move at the speed of the travelator if you're just standing still. If you decide to walk with the travelator, hell yeah, your walking speed plus the speed of the travelator is going to be your total speed. So cool. So that one, and then why do I spend so much time on something super easy? You might just be saying like, well, just get on to the next problem. And it's because, well, even from that, so this video is going to be kind of 2 parts. One, we're going to use kind of my axiom is like the units are the equation. Since we're dealing with velocity, we have meters per second. We're also dealing with time and seconds, and we're also dealing with, hey, distances. So the next problem is going to be, hey, we're going to move a certain distance along the and then so if we have these 3 things, the units kind of are the equation. If we have meters divided by seconds, well, cool. If we just divide those 2 things, distance and time, we're going to get meters per second. Also, if I have my velocity in meters per second and I have distance, it's a little bit harder, but we're going to take that distance and divide by meters per second. Meters are going to cancel, seconds going to pop upstairs, and that'll give us seconds. Cool, so we kind of have 3 different things. We can play around with those. Alright, so the other aspect of these relative velocity problems is, just using your intuition of being like, oh, okay, I see what's going on. If I'm on this travelator and I'm walking at a speed of 0.3, I get to add the speed of the travelator. That's going to be my total speed in that direction. So even just right there, we have an equation. We have the speed of the travelator, we have our walking speed, and throughout this problem, this V is going to be the speed of Malachi, so maybe Vm of Malachi, and this W is going to be the speed of the travelator, maybe Wt, and cool. This is going to be our total speed. And then it's like when we do relative problems, it's like, well, total speed relative to what? Because if you're in an airport, your kind of goal is to get like maybe over there. And so if you're going with the travelator, well, hell yeah. Now your total speed is going to be 1 meter per second. And, relative to the ground, you're going to, like, that's the speed you're actually going to get there. Yeah. Alright, so I use this strategy, you know what I mean? I first say, like, can I do anything with the numbers that makes sense? And then I go back and see, what did I do to those numbers? And are those numbers, part of an equation? And I don't know, it works for me. So we're going to get on to the second question, also probably pretty easy. It says the group that was walking stops to read a sign. Malachi is still on the travelator. So how fast must Malachi walk now to stay with the group? And so if the travelator is moving at a speed of 0.7 meters per second, and the group stops to, check out this sign, well, Malachi has to walk at a speed of 0.7 meters per second. And if the group was walking this way at 1 meter per second, Malachi was, from problem 1, was walking at a speed of 0.3 meters per second to keep up with the group. The group instantly stops, and so Malachi is going this way. Whoa, Malachi has to stop, but then Malachi is still moving with the travelator, so has to walk the other direction. So we're going to have a negative 0.7 meters per second. And maybe number 2 is just, hey, how fast must Malachi walk? That's going to be 0.7 meters per second. But you could also specify maybe in this negative direction. If we're calling this the positive direction, where the travelator is headed, and this is the negative direction. Okay, sweet. Okay, so now we're going to move on to the actual meat of this problem. We have problem number 3. There's going to be 4 problems to this. Okay, so problem number 3, it says the group moves with 1 meter per second towards the left. The travelator in this problem also moves to the left. Okay, and cool. And the travelator moves at that 0.7. So the travelator moves at 0.7. The group moves to the left at 1 meter per second. Malachi walks at a constant speed relative to the ground. And travelator beneath him. Yes, it's kind of interesting. You can just imagine that Malachi can walk at a constant speed. Whether he's on the ground or the travelator, he's going to walk at just this constant speed. We're going to call it V. Okay, so this is the path that Malachi is going to walk. The travelator is moving this direction. And so you can just imagine that if Malachi walks this way, he's walking against the travelator. So it's his progress in this direction, if he was in an airport, is going to be kind of slow. But then once he gets to 10 meters, he's like, and this travelator could go on, or it could just be this length, doesn't really matter. But once he gets to the end of this travelator right there, he's going to instantly turn around and then keep that same speed and then walk this direction, and he's trying to get to point A. Cool. So now it says, what does it say about the group? Oh, and it just says the Malachi and the group start at this point right here, kind of the halfway point in the middle of the travelator. And the group is going to start walking this direction with a speed of 1 meter per second, and they're going to walk towards the left. Okay, and then Malachi is going to do this. Now it says that, Malachi wants to arrive at point A at the same time as the group. So Malachi is going to walk this way and then this way. We know that when Malachi walks this way, his walking speed plus the travelator is going to, make him move way faster. And so, cool. So he can walk this way and then walk this way and still catch up. Heck yeah. And just so this problem makes, just relative sense, is just like, does it make sense if this is the group and they're going to walk this way, but then this is you and you're just like, well, I'm actually going to, and then let's say this is just 2 city blocks, so this group's going to slowly walk along this city block, at a nice casual speed, looking at the window fronts, but you're like, oh, hell yeah, I'm going to actually run to the end of this block and then come back, and I'm going to meet you guys at the same time. So this wouldn't involve a travelator at all. But you could imagine you could do that. I mean, let's say they're just taking a step every 10 seconds. Well, you could probably get to the end of the block and back after they took about 10 steps or less. So that's the first check on reality that I do for problems. Is like, well, does the problem make sense? Is it physically possible for someone to travel in a different direction and then come back and then arrive at the same time? And so that answer is hell yeah. Okay, so now I'm going to go over how I kind of slowly solved this problem. Is like, do I know anything? And the first thing that I know that's obvious to me in this problem is just the group. The group is moving 1 meter per second this direction. They have to move 10 meters per second. And so they're going to arrive at this time at a certain time. And again, so this is where I say the units are the equation. We have meters per second. We have meters. And what do we want to know? We want to know seconds. And so what do we do to these two things to get seconds? If we multiply them, we would get meters squared per second. That doesn't make any sense. If we took meters per second and then divided by meters, well, we'd have meters would cancel, but we'd have 1 over seconds. This still gets you the right answer. You just have to invert it. You got to take it to the -1. So we're getting closer. But yeah, it's intuitive when you're just like this is how crazy it is. Like, this is the equation involved where you have to take meters per second and then divide it. I'm sorry, I'm messing it up. Meters divided by meters per second. And meters will cancel, seconds will pop upstairs. So this is the definition of, hey, like distance divided by velocity is going to be time. Okay, why can we do that so intuitively? Because this is the whole point of making this video, is like, our intuition is pretty darn good. So, use your intuition and figure out what you're doing to the numbers, and then just realize the numbers probably are an equation. So, if I'm traveling at a speed of 1 meter per second, and I got to travel 10 meters, how long is that going to take? And it's going to be 10 seconds. And let's really double down on this. Let's say, so my speed is 1 meter per second. I don't know. It's like we don't typically, I'm in America and we don't typically use meters per second. Even if you're driving in a car in metric countries, you're still going to be driving in kilometers per hour. But if I'm traveling 1 meter per second and I travel this speed for 1 second, how far did I go? Well, I traveled 1 meter. Cool. So if I'm traveling at a speed of 1 meter per second for 1 second, traveling 1 meter. Cool. I need to travel 10 meters. Nice. It seems like it's going to take me 10 seconds. All right. Excellent. All right. And hell yeah. And yeah, that's the interesting thing about velocity is like we all drive in cars. We all drive at constant speeds on the freeway, and we all know how far we need to drive, and then we just intuitively know how much time it's going to take, and it's just fascinating. So we do have an equation for velocity. I probably should write that down. Velocity is change in position, change in time, kind of the technical definition. And I probably would write the definition of acceleration. It's going to be change in velocity, change in time, but this problem doesn't involve any acceleration. I would write it first though. Acceleration is change in velocity, change in time, just so you know that you can also write velocity as change in position, change in time. Cool. And hell yeah, and that's as far as you can go. There's no subset after that, because the units on acceleration are meters per second, and that's where the units are the equation. It's a change in velocity in meters per second for every 1 second, and you could say that's a change in time of 1 second. Alright, sweet. Same thing for position. Velocity is a change in position in meters divided by a change in time of 1 second. And so that's going to be the units on velocity is meters per second. Now these equations, if like the caret indicates a change in velocity, a change in position, and a definite change in time. Maybe if you take a whole change in time of 1 second, your position is going to change. And so these are legitimate equations as long as this side is constant, so a little bar on top. If your acceleration is constant, well, I should say the bar is like an average. So as long as you're taking the average velocity or the average acceleration, this equation definitely applies for that time frame. And hell yeah, I don't mind going over this, because if I have acceleration as a function of time, like if it's gravity, it's just going to be like a constant 10 meters per second per second. But let's say we have something that does this, you know what I mean? It's kind of slopey, and then here's our time from 0 to 1 seconds, and I want to know, like, oh yeah, and then back. All right, so I want to finish up kind of soon, but just with this little topic. But I guess what people don't realize is that this is now an equation of 3 things. I can rearrange this 3 different ways. So right here I've solved for acceleration. Maybe I want to solve for the change in velocity. Well, that's going to be the acceleration times change in time. Just know that it's either the average acceleration, or if it's constant, cool, you're just good to go. And so, cool, now we solve for the change in velocity. Maybe I want to solve for the change in time. Bring change in time upstairs, and then we got change in velocity divided by acceleration. So we got 3 equations to figure out what we want. And so if our acceleration isn't constant, but you just take the average, you know what I mean? So maybe between there and there, it's just like that's our average right here. So if this was 10 up here, maybe, and this was 5, maybe my average is like 8. Cool. So I'm going to then use that. So I know my acceleration is 8. I know my change in time is 1 second. So now what can I find? Well, this is an equation of 3 different things. I know that one and that one. I can find change in velocity. So let's go down here. I can say 8 times 1 second, and the units, probably match up, and we have a change in velocity of 8 meters per second. Cool. And we can run through that same process with this velocity equation. And we have 3 things, and we have velocity so this is our first one. We can also solve for change in position. That's a velocity change in time. That's our second one. We can also solve for change in time. That's going to be, so change in time is going to pop upstairs. This is going to pop downstairs, and booyah. And as long as for our problem, everything, like all the velocities chosen are constant. So I can get rid of this average sign, and so we can say velocity is change in position, change in time. Change in position is velocity change in time, and change in time is change in position times velocity. So yeah, it's just kind of good to know that you have 3 equations. Now I'm typically, for this problem, not going to use these from like an equation perspective. I'm just going to use them from intuition back to, hey, I'm going 1 meter per second for 10 meters. I'm going for 10 seconds. I think that is, just know that there is equations, and also why I brought this whole process up, because when it comes to velocity, I think it's just so intuitive. If I'm traveling 1 meter per second for 10 meters, I'm traveling for 10 seconds. But maybe we're overlooking where that equation comes from. Like, why do I know my change in time? That's going to be this one. Yeah, like even me is just like, oh, I didn't even realize that. Yeah, my change in time is going to be my change in position of 10 meters divided by 1 meter per second. And it's just really fascinating to me that especially with the easier things, when it comes to velocity, we just have a really strong intuition, but we might forget that there's equations associated with that. But then when we get into something just a tad more difficult, when we talk about accelerations, whether they're constant or finding the average, and then what that means, you know what I mean? I can actually find the change in velocity, which we just did with this equation. Then it's less intuitive. Then it really feels like we need an equation. It's just kind of fascinating. Alright, hell yeah. So for this problem, we got the first part. The group's 1 meter per second for 10 meters. When they get here, it's going to be a time of 10 seconds. So now here's the aha moment that people should have. It's that Malachi only has 10 seconds to do whatever he wants to do. You know what I mean? If Malachi is going to meet the group at point A when the group gets to point A, Malachi better get there in 10 seconds. So in physics, that's going to be called your continuity. You know what I mean? That's whatever Malachi does, the time that Malachi does that has to be 10 seconds. So now this is, for these relative problems, this is where I would just, guess. You know what I mean? Yeah. And so we have the travelator moving this way at 0.7 meters per second. It's always a fun one to be like, hey, let's say Malachi is moving. Malachi just starts walking at 0.7 meters per second that way. Not in a total distance. No, just imagine Malachi closes his eyes and is like, yeah, I know what it feels like to walk 0.7 meters per second. And so that's what Malachi does. And great. He's just going to stay there. So this is anytime you get a relative velocity problem, I always would mentally say, well, what's not going to make sense? You know what I mean? So, and then obviously the other constraint is Malachi has to walk to the end. If Malachi doesn't walk to the end and get back to the group, then the problem doesn't make sense. Malachi can't just not walk and then just just go down the escalator and then meet the group at point A. Part of the problem is that it's kind of a challenge. Malachi has to get to the end, reach the end, get back at the same time. Cool. So now we know that if Malachi walks at a speed of 0.7, he's just going to stay there. He's never going to get to point A. He's never going to get up here. So let's choose 1.7 meters per second. So Malachi is going to walk at a speed of 1.7. Again, the travelator is moving this way. And so if Malachi closes his eyes, knows what it feels like to walk 1.7 meters per second, well, the travelator is moving this way. So Malachi is only walking at a speed of 1 meter per second. And so how long is it going to take him to get to here? Well, it's going to take him 10 seconds. But at that point, the group is already right here. All right, hell yeah. So this is the process that I go over. You know what I mean? Just kind of one step at a time. And I think that the hardest thing for especially intelligent people, trying to learn math and physics, is the impatience of not wanting to do 10 calculations. So I don't know if I'm going to, kind of make that as an axiom, but, you know what I mean? Can you do 1 through 10 calculations that are very basic or very easy? Because now we can just, I don't know. So let's just ramp up the speed. So Malachi is now going to walk 3 meters per second. And, well, we were walking 1.7. Yeah, I'm chill with that. You know what I mean? So, so now what happens? Well, this direction, Malachi's speed is going to be reduced. We're going to be 3 minus 0.7. So we got 3.0 minus 0.7. Malachi's speed this way is going to be 2.3 meters per second. All right, so And, oh, and then, so this is where, like, I wouldn't do this. It's just like, nah, that seems too confusing. It really was nice to get this relative speed to be a whole number. So now let's have Malachi's new relatives, not relatives. Well, I guess it is a relative speed. But yeah, that's the thing with these problems, is just like, forget the kind of the technical language. Just go by intuition. So I want, like, if you're on this escalator, maybe you want to walk at a speed of 2 meters per second. Yeah. So if you're walking, yeah. Oh yeah, this is tripping me out. So yeah, physically, like, hey, if there's a painting right here at the airport, and then here is the end of the escalator, that's 10 meters. This velocity has to be relative to the Earth. So yeah, it is kind of good also to include kind of that language. You know what I mean? Not dismiss it, but yeah, so I want to walk 2 meters per second relative to, like, that painting, or just relative to the Earth. I basically want to get from here to there, which is 10 meters, and I want to have a speed of 2 meters per second. Cool, so let's do it. We have this speed of 2 meters per second, and we have to travel 10 meters. So what's our time frame? And so you could probably easily say that's like 5 seconds. And the equation to get there would be 10 meters divided by 2 meters per second. Meters cancels, and second pops upstairs, and we got 5 seconds. And then just keep in mind that this is the equation that we'll come back to. All right, hell yeah. So we're doing pretty good. We actually got here in 2 seconds. To have this speed of 2 meters, we had to walk at a speed of 2.7 meters per second. So if Malachi walks at a speed of 2.7 meters per second that way, the travelator is reducing his speed by 0.7, so that's where we got this 2. He gets here, and he's still walking at a speed of 2.7, so keep that in mind. But now the travelator is helping him, you know what I mean? So now his speed is increasing by 0.7 meters per second, and so his total speed is 4.4. Did I get that right? No, 3.4. Sorry about that. Is 3.4 meters per second. Cool. And then to get from here to there, and that's the relative speed, basically relative to this new painting. To get to the finish line, to the end, it's a distance of 20 meters, and the relative speed is 3.4 meters per second. You know, I mean, and then it's relative to what? Relative to the ground. You know, Malachi can walk 2.7. The travelator is helping him increase his speed by 0.7. And that's where, I don't know, these problems, I would just take it in bite-sized chunks. You know what I mean? Like, always, never lose the intuition of what makes sense, you know. And so for this problem, again, the problem statement is Malachi is walking at a constant speed, and so and even on a travelator, we know this from Newton's laws, that as long as you're walking at a constant speed, you can't tell. If you're walking at a constant speed, you can't tell. If you close your eyes, you can't tell how fast you're moving relative to anything else. Like, we're literally walking across the Earth and maybe going, you know, 1,000th the speed of light through the Milky Way or whatever it is. You know, it's like maybe it's 10,000th the speed of light. But yeah, we're just all sorts of, you know, even traveling 1,000 miles per hour, you know, around the equator. You know what I mean? Or if I'm at 45 degrees latitude, you know, I'm you know, my velocity relative to the center of the Earth. All right, so it's about 700 miles an hour. You know, 700, 800 miles an hour. Okay, sweet. So for these problems, I would never lose the intuition, but we slowly want to gain like an idea of, well, how did we, because we're almost there, you know, cool, I'm traveling 3.4 meters per second. I think we get that. And I have to travel a distance of 20 meters. Okay, so now let's use that units are the equation and go for it. So I'm going to take 20 meters and I'm going to divide by 3.4 meters per second. I'm using the meters as the equation just to make sure I did it in the right order. Seconds pops upstairs. So I have 20 divided by 3.4. I guess I'm going to pull out my calculator. And we have a time of basically 5.9. 5.9 seconds. Cool, so let's go back to how long did it take to get to here? It took 5 seconds. And it took 5.9 seconds to get to there. So it's a total time of 10.9 seconds. The group got here at 10 seconds. So just right away, it was just like, whoa, we almost kind of figured out the problem. You know, like that ain't half bad. I'm going to walk at a speed of 2.7 meters per second. It's going to take me 10.9 seconds to get there. The group's going to get there first. So, you know, even just something like that is like, doesn't that mean that I need to increase my speed? And so this is exactly how I solved this problem an hour ago. You know what I mean? There's no other way that I'm going to solve this, or I'm going to go through these steps, because these problem-solving steps will be useful for harder problems. And this is the technique of like, well, you know, use your intuition, figure out what you're multiplying, dividing, adding, and subtracting, and then see if there's an equation there. And so now we're going to start that process. I'm going to choose my speed of 2.8 meters per second. Okay, I got to get this 10 meters, but the travelator is reducing my speed by 0.7 meters per second. So like my speed this way is only 2.1 meters per second. Hell yeah, I need to travel this distance of 10 meters. I'm going to go back to this equation where the units are the equation. Well, I got to take that 10 meters and divide it by 2.1 meters per second. And even right here, I'm just relying on axioms where it's just like, does this make sense? If I'm traveling 2.1 meters per second and I need to travel 10 meters, like how long is that going to take? Well, let's just do it for 1 second. In 1 second, I'm going to travel 2.1 meters. Sweet. And that's approximately 2 meters. So, and I got to travel 10. So I need about 5 seconds. But I'm traveling a little bit faster than, you know, so it's going to be like 4.8 seconds. I don't know. You know what I mean? Always do that too. You know, and we'll do that all honestly towards this end of the video, because I made a, like anytime we're working up to getting a quadratic equation, and I make so many mistakes with the quadratic equation. I always want to find like a different ways to get to the answer without from an intuitive process. And we kind of just did. Like, hey, we're pretty close with 2.7. We're trying 2.8. Okay, so let's do this. So we have 10 divided by 2.1, and we get a time of 4.76 seconds. Hell yeah. Okay, so now we're having this constant speed of 2.8. We turned around, and now our speed gets to increase. Our 2.8 meters per second, we get to add 0.7 meters per second. This is going to be 3.5 meters per second. All right, sweet. And we need to figure out how long it's going to take to get from here to there. So we're going to have 20 meters divided by 3.5 meters per second. Okay, so 20 divided by 3.5, and we get 5.71 seconds. So let's add these up. Maybe we're pretty close. Okay, so that took 10. So 10.47 seconds. Hey, that's getting better. This was 10.9. Now we're 10.5 seconds. Okay, so and it's kind of cool. Like and then this is another good thing to do, especially if you're just kind of guessing and then re-guessing. So it looks like we were at 2.7 and our time was this. We went to 2.8 and we kind of got this 0.9 went to 0.5. So yeah, we're on the right track of saying, well, let's do 2.9. So we're going to do a velocity of 2.9 meters per second. Going this way, we're going to be at a loss of 0.7 because the travelator is moving that way. So our relative speed is 2.2 meters per second. We need to travel a distance of 10 meters. What do we do to these numbers? We do 10 meters divided by 2.2 meters per second. 10 divided by 2.2, and we get 4.545 seconds. Okay, hell yeah. Now on the return trip, we're going to have 2.9 meters per second plus 0.7. Alright, so we get 3.6 meters per second. We have to travel a distance of 20 meters all the way back to here. And so, cool, we're going to be 20 meters divided by 3.6 meters per second. 20 divided by 3.6 is going to be 5.5. See, that's why, and then let's talk about this, because that's why in the beginning I wanted my relative velocity to be 1, my relative velocity to be 2, because it was just kind of easier to see how long it would take to get there. And even though on the return trip, yeah, so if I was traveling 2 meters per second relative, it's going to take 5 seconds. But now I'm traveling, let's say I'm traveling 3 back the other way. And so I'm traveling 3 meters per second, and I got to travel 20 meters. You know what I mean? Just change it to 21 meters, and you can be like, oh, okay, I see it. You know, if I'm going to travel 3 meters per second, that's going to be, 7 seconds to get 21 meters. So it's going to be, so in that case, 5 seconds this way, 7 seconds that way, total of 12 seconds. So just using those guessing skills, making the numbers mentally easier to compute in your head, for those first calculations is very useful. Because now when you get into here, my mind isn't trying to do this. I'm not trying to divide 20 by 3.6. You know what I mean? But I could. If I had 3.5 goes to 7, and then double that goes to 14, and then add another 7, and I get 21. Oh, okay, so that's going to be 2 seconds there, another 2 seconds, another... So it's going to be about 6 seconds. And that's the answer I get. So it's just kind of a cool way to double check the reality. And so we're going to add these two numbers. It's going to be our total time. And so we have, hey, we're doing pretty good. And so we have 10.1. Is what we thought, 10.1. I feel like I messed up, but maybe I didn't, just because I've done this problem before. No, we're good. Yes. Yeah, so it took 10.1 seconds to get to point A, and the group got there in 10 seconds. So we need to increase our speed more. Now we just went from 10.9 to 10.5, now we're at 10.1. So do we need to increase our speed very much? And this is cool. I'm going to print off another sheet of paper, because now our process that we're going to do is what did we do? We did a lot of calculations. We did a calculation here to get our speed. We took our velocity of 2.9. We subtracted 0.7, so we did that one. We got this, and then we did this equation. Cool, then we did that. And then we put that aside. Then we said, hey, our speed's going to increase on the way back. We did this equation. We used this velocity, but with this distance of 20, and did this. And then you get, another answer. And then we added these two things up. So that's kind of cool, because we can get just one equation that does all of that. And so that's kind of where we're headed. Let me print off some more sheets of paper. Alright, hell yeah. So, yeah, let's do the equation. So we chose a velocity of 2.9 meters per second. And the first thing that we did was subtract 0.7. And so you don't even have to use variables. We can just say 2.9 minus 0.7. Hell yeah. And then we took that answer, so let's put it in parentheses. And then what did we do with it? Oh, well, we took 10 divided by it. Oh, okay. So I'm just going to do this and then put 10 on top. And hell yeah. And didn't that give us a time? And then what did we do to that time in the end? We added it to something else. Okay. So maybe you can't see that, and you just, well, now I take my velocity of 2.9, and now I'm going to add 0.7 plus 0.7. Cool, and this is going to be my velocity this way. I need to go 20 meters. So I got that velocity. What did I do to it? I took 20 and divided it by it. Sweet, so now I do 20 divide by it, and then I get that answer. Okay, and then I added both of these together. Oh, sweet. So there's my equation. And then what does that give us? That gives me the time it's going to take me to get to point A. Alright, so that's going to be my first variable I'm actually going to write. T of A is going to be this, 10, 2.9 minus 0.7 plus 20, 2.9 plus 0.7. And I don't know, I would just rather spend the rest of my life taking a problem like this and doing it this way, just kind of intuiting it, seeing why that velocity is helpful, or it hinders this way and then it's helpful that way, how that gives me a time here, a different time there, and how those added times together, instead of just memorizing this equation. Because so now let's rewrite this. So this is going to be the time it's going to take Malachi to get here. 2.9 minus 0.7 plus 20, 2.9 plus 0.7. Okay, and then let's go back to the group, because even the simplest things, there's still an equation to that. The group had a speed of 1 meters per second, and they had to travel a distance of 10 meters. And I just said that was going to take 10 seconds. And so cool, we have this 10, so we have 10, and then this 1. What do we do to these two numbers to get 10? Well, I mean, you could say we multiply them, but we could also do 10 divided by 1. So you get into that situation of like, well, maybe it's not so obvious what the equation is. So that's why we use that units are the equation. We have meters per second, and then we have, that's our speed, and then we have our distance in meters. And so we got to take that distance divided by the velocity. And don't overlook that. That's why I'm kind of constantly saying this, is because in this problem, I don't think it's not as intuitive. Let's see, what would be intuitive? Intuitive would be like, hey, I have 10 meters and I need to get there in 5 seconds. What's my speed? Well, then you can just kind of divide those. I don't know, that one's a little bit easier. But when you're taking velocity, when you're taking distance and dividing it by velocity, I know that is kind of just like the tricky part. But it's not too hard when we have 10 meters and a velocity of 1 meter per second. But yeah, it's interesting. Intuitively, you can say I have a speed of 1 meter per second. I can get 1 meter in 1 second, so it must be 10 seconds to get 10 meters. That's kind of the intuition on that. Where the units are the equation, I have this distance in meters, velocity in meters per second. I have to divide these so second pops upstairs. So my equation for this time, so for the time of the group, so time of the group to get to point A is going to be that 10 meters divided by 1 meter per second. Cool, and that's going to give me 10 seconds. So let's write that in. So this is the T of A for Malachi, and this is the time to get to point A for the group. And now we have an equation for the group. Still no variables. You know, a lot of people just say, hey, start with variables first. I'm going to say do the opposite. Use your intuition with the numbers. What do you multiply and divide? And then build your equation still with the numbers. Okay, because the time it took to do that was going to be that 10 meters divided by 1 meter per second. You know what I mean? And sweet. All right, hell yeah. And so the part of this problem, the continuity part, is like, hey, both the group has to get to point A and Malachi has to get to point A at the same time. So if this is the time, and we just did this one and it was like 10.1 seconds, it was pretty close. And this was 10 seconds. Okay, so the continuity is like, hey, these times have to be the same, so we could write this equation. time of Malachi to get to point A, has to equal the time of the group to get to point A. Yep. And then from an equation perspective, is since these are equal, this side of this equation has to equal that side. So then we can just write this. We can write 10 divided by 2.9 minus 0.7 plus 20 divided by 2.9 plus 0.7 is equal to 10 divided by 1. And this is actually going the extra mile to say this is 10 divided by 1. I didn't do that the first go around. I just said it was 10. But this was actually helpful. The more that you can, see how did we get this time? Well, we took something we knew and then divided it by another thing that we knew. So, like, keeping that order, or that is going to be helpful, because problem number 4 kind of wants us to dive into that, knowing that, hey, this is a distance and this is the velocity of the group. All right, so now we're going to put variables on it. And we don't have to put variables on everything, because we already know the group is going to walk at a speed of 1 meter per second. This distance that the group has to walk is 10. The first distance Malachi has to walk is 10. The second distance Malachi has to walk is 20. Those things aren't changing. The travelator's speed is 0.7. So you could put, right now you could put a variable on everything, but I didn't do that. The only thing I put a variable on was this thing. This is the only thing that I'm interested in changing to equal, so I'm going to do these two things to equal 10. Alright, sweet. And for this problem it says Malachi's speed is v, so that's what we have right there. And so let's write our equation. So we're going to have 10 divided by 2.9 minus v plus 20 divided by 2.9 plus v is equal to 10. And I'm just going to remove that for now. Alright, so hell yeah, this is our equation. And whatever, I totally messed it up. No. This is Malachi's speed 2.9. So sorry about that. So we have 10 divided by v minus 0.7 plus 20 divided by v plus 0.7 is equal to 10. And we're going to grab a new sheet of paper and write this. So we have 10 divided by Malachi's speed minus the speed of the travelator. 20 meters divided by Malachi's speed plus the speed of the... And so this is so important. Because we played around with this problem even enough up to this point, this thing makes sense. Well, yeah, that distance of 10 divided by the slower speed, that's going to be the time frame. And then on the way back, it's going to be that 20 meters divided by, that quicker speed. And that's going to be that time frame. And both of these have to equal 10, and that's what we have over here, equaling 10. Alright, hell yeah. And then so we're going to use some math. Like, there's kind of a cool way, because we want to add these two things together, and we need the denominators the same. Once you get the denominators the same, then you're just in, because you can get a quadratic equation and you can solve it. But this is the way that I'm going to solve this, because it's we already got pretty close. That Malachi's speed is pretty close to 2.9. So in my calculator, I'm going to just do this. I'm going to go 10 divided by 2.9 minus 0.7. This is, I'm just doing this verbatim of kind of how I solved this an hour ago. And then we got Malachi's speed of 2.9 plus 0.7. And so cool. So now we got 10. And instead of just writing this out a bunch of times and changing that velocity, we can just change the velocity in our calculator. So now I'm going to go up to 2.5. And then our speed got reduced to 9.9. So if Malachi's speed is 2.95 meters per second, Malachi will get there too soon. Okay, so it's always good to kind of state what's going on, especially if you're kind of changing variables. Okay, so let's just go to 2.2 meters per second. And that's going to be 10.03 seconds. Okay, it's still going to be a little bit slow, so let's go to 9.3. Okay, hell yeah. So that's going to be 9.99 seconds. So Malachi will get there faster at 2.93 seconds. And at 2.92, this is going to be too slow. So too slow, too fast. Even though like we're really close to the right answer. You know what I mean? But so keep that in mind. And then now here's the other technique that I will use, which can be very helpful, especially, I don't know, just because like right here is like the least amount of place where you're going to make mistakes. It's like the second you start to do the math on this and get a quadratic equation, I made errors, and that was kind of a bummer, but I could go back to this and I caught my errors. I knew the answer had to be between 2.92 to 2.93. So I would say that's pretty accurate. You know what I mean? 2.925. You know what I mean? And so let's so what I'm going to do is I'm going to throw a variable in my calculator as x for Malachi's speed. And so here we have, and I can change that value of x. So I'm going to be 2.925 stored as x. And now I can see, okay, that's too slow. I need to increase it. So I'm going to bring that back up. I'm going to go 2.927. All right, still too slow. 2.928. All right, still too slow. 2.929. Whoops. All right, so hell yeah. So it wasn't close to that. It was close to 2.929. It was actually closer to 2.93. Okay, hell yeah. And we can just, I find it fascinating to do this technique. I don't know, it's kind of therapeutic, because I can just be like, okay, let's do 2.9295. And too fast. All right, 2. All right, too fast. 1. So we might, so 2.929 was actually too fast. So we need to go 2.9285 maybe. All right, that's too fast. All right, there you go. It's too slow. Whoops. So we need to increase this speed. All right, now we're too fast. So 2.9282 is too slow, and 2.9283 is too fast. So there you go. I can for sure 100% positively say Malachi's speed has to be 2.928, and that's within 3 significant, and that's ridiculous. You know what I mean? Like obviously it's just 2.9, close enough, 2.9 meters per second. That's the speed of Malachi. But it's just fascinating because when we get an exact answer using the quadratic equation, you know, we can use this to double check our answer. Okay, so here's the math involved. To get the denominators the same so we can actually add these, I have to get the denominators to look the same. I have a v minus 0.7 over here. And so I need this term as well. So I need a v plus 0.7 in my denominator. But I can't just do that without multiplying by the top by 0.7. And then this whole thing is just like multiplying by 1. It's kind of fascinating. And then over here I'm going to have v plus 0.7. I need this, v minus 0.7. But if I do that, I also have to multiply by the top by 0.7, because this is going to be just a unit value of 1. And then so I'm going to have 20 and then 10. Alright, hell yeah. So the bottom is going to be the same. The bottom is going to be this v minus 0.7 multiplied by v times 0.7. We can FOIL this through. It's going to be v squared. I'm going to have plus 0.7 and then minus 0.7 v. Oh, sorry, v. And then I'm going to have negative 0.49. That's 0.7 times 0.7. These two cancel, and I just get v squared minus 0.49 for this bottom term. Okay, hell yeah. And I probably should have done this down here, but yeah, let's do it one more time. So that's kind of the process. Always good to do it again. So we're going to have 10v plus 0.7, especially if you can just kind of do it intuitively. And then I'm going to have v minus 0.7, v plus 0.7, plus 20v minus 0.7, and then v plus 0.7, v minus 0.7. So this is the thing that's just multiplying by 1, and it just kind of, it doesn't disrupt the equation at all. But because we did it, our denominators are now the same. We're going to have that v squared minus 0.49 on the bottom here. Up top, let's do this. This is going to be 10v plus 7, and this is going to be 20v plus 14. 20 times 0.7, well, I don't know that, but I do know that 10 times 0.7 is 7, so double that's going to be 14. All right, booyah. And right here I'm going to have 30v plus, oh, and then I'm sorry, this is negative. So this is minus 14. So I'm going to have 30v minus 7 after all that. So we're going to have 30v minus 7. But just see, like I didn't even, the error that I made was, I just said this was 10, so I made that error. And then I even went back and then changed this to 20. But I also made the error, you know, when I multiplied these together, I thought I was basically just multiplying like v plus 0.7 squared, and so I did that instead. You know what I mean? So it's just kind of fascinating, like where we make errors. Okay, so we did this process. We FOILed the top through, and then added both those two terms because we could do that. We could finally add them because the denominators are the same. After foiling the denominators, this is what the denominator looks like. This thing is still equal to 10. And I was getting really excited here because I thought I was going to be able to do some long division. I just saw that you can do long division on like polynomials, and I thought that was kind of fascinating. But now I racked my brain and I was like, no, you just multiply this upstairs. So I'm just going to do write less steps, and I'm going to do v squared minus 0.49. And so I just brought that upstairs. That's all that I did. Let's FOIL this through. This is going to be 10v squared minus 4.9. Okay, so now I have this equation. And let's get everything to one side and make this side equal to 0. So 0 is equal to, so we have a 10v squared. We're going to have a minus 30v. And then we're going to have, this is going to be a 7 plus, it's going to be a 7 and then minus, or adding a negative 4.9. I just saw this as negative 5, so that's 7 minus 5. That's going to be a positive 2, but we're not going to subtract that much. We're just subtracting 4.9. So that's how mentally I could see that this was 2.1. Cool. So we have plus 2.1. All right, hell yeah. So now we can do the Pythagorean's theorem. And I might just stick on this page. Because instead of doing, what did I said Pythagorean's, I'm sorry. We have to do the quadratic equation. Now, I hate the quadratic equation because the quadratic equation gives you like something plus or minus the square root of something divided by 2a. You know what I mean? So it's just like, it's not even a nice format. So my MO is going to be completing the square. And so let's go over that, because this is a good time to see how fast I can actually derive the quadratic equation. And I think anytime you're going to use the quadratic equation, you should derive it. It's kind of one of the coolest things to derive, and it's the only way that you're going to be able to complete the square, and it kind of proves how you can complete the square. First thing is we don't like this ax squared. We just want x squared. So we've got to divide everything by a. So we're going to have b over a plus c over a is equal to, well, 0 over a, that's still just 0. All right, let's get this to the other side. X plus b over ax is equal to negative c over a. And I can actually do this in one step. I can be like, hell yeah, x squared b over ax, and then get the c divided by a over to the other side. So we're going to have a c divided by a and then a sign change. You know what I mean? So that's kind of cool if you can do that all in one step. Or I mean, I'm just saying like how I'm able, like my strategies. And then right here, I know that this is going to be, we're completing the square. So we're going to have x and then half of this. And, you know what I mean? Just guess if you kind of forgot whether it's got to be double it or half of it. But even just that, I mean, you know that this, I mean, you should remember that it is a factor of 2, right? Like this, you can't just say this is x plus that term. You know what I mean? So even if you forgot whether it's 2 times this or 1/2, I think for guessing skills, it's just good to, and I'm going to work on this, just like, you know, just when I do like 45 plus 17, I don't know, it looks like 62. You know what I mean? So I think that is a good thing to do. 117 minus 31. I think that is 86. You know, probably not. Like, but that's all I could think about. And like, did I get it right? 3, 11. See, I have 3. Oh my God. 3, 4, 5, 6, 7, 8, 9, 10, 11. 86. It's really bizarre. And then, so there was a great comment I kind of wigged out the other day on one of my videos because, yeah, someone's like, you should do it this way in these like 10 orders. And I was just like, whoa, that's a lot. You know what I mean? Because, like, I'm doing this problem from the opposite of that. I'm doing this problem where everyone can handle it. Everyone can intuit the velocities and then make many equations and then realize that those many equations are make one equation. But I think even the way this looks, this is cool because you're just like, whoa, I didn't know, like, there was this cool equation to describe this motion. And, yeah, it's fascinating. So I think this was also part of those 10 steps, is just like ditch the calculator, work on, and then one way to ditch the calculator is to, and then one of my strategies has always been to just go with an intuitive guess and then work backwards and see what error you made, or see how close you got. Because, yeah, this blew my mind that I was able to intuit that. My mind went blank. But we got the right answer. All right, hell yeah. So back to here, sure, divide by 2, who cares? And then because you're going to double check anyway, because like right here, then you're going to FOIL it through. And then when I do, and this is the definition of completing the square, where you just have one square term. And so how I do this, I do this as x squared, and then I'm going to square this. And I'm getting better at like, well, at least put it over here. So we have b squared divided by 4a squared. And then the middle term is going to be this times this, but I'm going to have 2 of them. Oh yeah, no duh. So that's b over ax. And if you can't see it, we have x, b, 2a, and then we're going to have 2 of those. So the 2's cancel, and we have x, b divided by a. And that's that term. So cool. We started with these 2 terms. We did not have that term. So we have to add it to this side. The second we add it over here, it's already implied that it's in here. Like this term is now in here. And then this side you have to add that term over there. So we have negative c divided by a plus b squared over 4a squared. And now, once we have it like this, I take the square root. And then that just drops out, and we just have those 2 terms. It's so amazing. Plus or minus, and I got to get better at this. All the pros is like, even the MIT students, like anytime the professor did a negative or a square root, I was watching the special relativity. All right, hell yeah, sorry about that. Got a new battery. But yeah, so in the special relativity lectures, the students were like, hey, you used a square root, so what does the negative, what does the negative root mean? And the answer was just, well, it's meaningless. So yeah, so in a lot of practical applications, when you have a square root, yeah, maybe one term is meaningful, and then maybe the other term is meaningless. And so that's what's going to happen. And the reason why I like to complete the square is because you don't have this form where you would have to, you're just going to get it in this. One term plus or minus the square root term. And then it's just easy to do. This requires 3 different calculations to see what answer you get. You got to do that twice for 2 different answers. Here, you just have this plus this or this minus that. So that's going to be your answers. And I don't know. I just think that is just a way better way to go. Okay, so here we go. So we took the square root of this side. Again, this is just all we have over here. And these are notes from above. But when we do that, we just have x plus b divided by 2a is equal to this. So let's just get it to the other side, and we'll get x is equal to this. Negative c over a plus b squared over 4a squared. Plus, no, I'm sorry, this has got to be minus b over 2a. Cool. And this is close to, our quadratic would say x is equal to negative b. Well, I see a negative b right there. Plus or minus the square root of b squared. Okay, I see a b squared over there. Minus 4ac. It's like, oh, I only see a negative c right here. But if we multiply by a negative 4a, if we multiply by 4a on both sides, oh, actually we have an a downstairs too, so I would have to multiply by 4a squared on both sides. You know what I mean? Then I would have a 4a squared down here and a 4a squared up there, and the a's would cancel, and I would just have minus 4ac up there. You know what I mean? So you get that 4ac term, and then all divided by 2a. Well, 4a squared is going to be now both of those. It's the same situation that we had here. To add these two things, the denominators have to be the same. And when we take the square root, the cool thing about square root, if I have the square root of 3/4, it's the same thing as the square root of 3 divided by the square root of 4. I can do those two things independently. And I can say, okay, hell yeah, that's 2. And if I have square root of 4a squared downstairs, same thing. If I have the square root of 3/4 a squared, that's going to be the square root of 3, square root of 4a squared. And this is another, just really good fundamental, is the square root of 4a squared is the same thing as the square root of 4 and the square root of a squared. So this is going to be 2a. Cool, and so that's where you get that 2a term. Alright, hell yeah. So, but I just think this is just such a, and it's not the most obvious looking thing. We have x is plus or minus the square root of negative ca plus b squared divided by 4a squared minus b divided by 2a. But you would still see where all the terms came from. This negative ca was that first step. Cool. Plus b squared divided by 4a squared. That was that something extra to complete the square. Minus b divided by 2a. That was this term divided by 2, which we needed. So just 3 terms that are kind of fundamentals of this proof of completing the square. And I would just rather use this term. I don't know how I would memorize this, but you don't need to, because now we're going to go through the process of doing this by the completion of the square method. So we're going to get this equation as 0 is equal to 10v squared minus 30v plus 2.1. First thing we're going to do is divide all these terms by 10. And let's get the 0 over here just to keep it similar to what we just did. So we're going to have v squared minus, 30 divided by 10 is 3. So minus 3v. This divided by 10 is just move the decimal place. So we have plus 0.21. Alright, hell yeah. And like I said, I like to do 2 steps at once. So this is minus 0.21. Okay, I was just kind of seeing if I did that right. Hell yeah. And then the part of the complete of the square is v. This has to be a minus, because our middle term, anyway, and then half of it. So we're going to have 1.5v. just 1.5 squared. And even if you're confused here, just use your best ability to guess. Yeah, for sure it's half that middle term, but then FOIL it back out. We have v squared. We're going to have this squared. I mean, we already have to FOIL this back out to get this extra term, which is just going to be 1.5, negative 1.5 squared, which is just 1.5 squared, and that's going to be 2.25. Man, I hate doing 15 times 15. I had to rack my brain again how to do it. How would you do it? I don't know. Like, I'm glad I made the video. I made this video on, like, 15 times 15 is also foiling 10 plus 5 times 10 plus 5 is kind of fascinating, where you do get 100. So I can see that. I'm going to say this is 10 times 10 is 100. And then I'm going to say it's 10 times 5 is 50. And then 10 times 5 is 50. And I can do that one in my head and be like, well, 10 times 5, and I'm going to have two of them. So I can just say it's 100 plus 100, and then plus 25. And so I do that. I can do that in my head. Let's do that. 17 times 17. That's going to be 100. 10 times 7 is 70. I'm going to have two of them. I'm going to have 140. So right now I got 240. And then I got to add 7 times 7 is 49. So this is 289. All right, hell yeah. And so let's go back to the foiling method. So we have the 100. We're going to have 50. We're going to have 50. And then we're going to have 25. So, cool. So we get 225. I don't know, yeah, it's just fascinating. You can do it with dissimilar numbers. You could do 13 times 16. This is going to be 100, but we're going to have 60 plus 30. That's going to be 90, and then 3 times 6 is 18, and so we're going to have 208. Okay, booyah. All right, so I basically need to get another sheet of paper after that tangent. So where are we at? We are just double checking ourselves on this. So this is v squared. We're going to have, I just wanted to square this term. It's going to be 2.25. Holy Toledo, that's where we were. And then we're going to multiply these two together. It's going to be a negative 1.5v. We're going to have two of them, so minus 3v. And then we go back up to here and be like, hell yeah, that's a check on reality. And then we pick up this extra term. We add it to this side, but we already did. You can add it to this side right here, but it's already in here. It's already in this perfect square. And then adding it to this side is 2.25. So we got 2.25 minus 0.21. This is going to be 40. So we got 2.04. Okay, hell yeah. So this side is going to be that 2.04. This side is going to be that square, v minus 1.5 squared. And now we can just square this side. Squaring this side gets rid of that. And now we have v minus 1.5. We're going to add that 1.5 over here, and we're just money. You know what I mean? We have our velocity is plus or minus the square root of 2.04 plus 1.5. And let's do this. What's the square root of 2? I don't know. It's like 1.4. So we have 1.4 plus 1.5. That's going to be 2.9. And we already have a check on reality. So that's so sweet that looks like we did everything right. And so let's throw this into our calculator. Square root of 2.04 plus 1.5. And obviously it's not the negative root. Negative 1.4 plus 1.5, that would be a velocity of 0.1. That wouldn't make any sense. And it's good just to be like, even the negative roots, you know what I mean? Can you get something that's 0.1 and make, and say why it doesn't make sense? Because if his speed is 0.1, he's just going to be moving backwards. He's never even going to get to this point. So that is kind of fascinating. Does that mean, that's interesting. I'm curious about that. Let's do the negative root first. So negative, well, let's do the positive root. So we got the square root of 2.04 plus 1.5. And sweet, we get 2.928. So our velocity of Malachi, 2.928. And I don't know. Okay, yeah, and here's where we had. It's we said it was going to be 2.928 in between 2 and 3. And so, booyah, we're 2.8. So that's in between 2 and 3. 20 and 30. Okay, so now, like, cool, we did everything right there. It was just such a cool check on reality. And like I said, I made all those mistakes doing this problem. It took me a while to actually link up this equation into just my intuition, just using my calculator and solving for it. Cool. So now let's see. And so, yeah, we got this. This was our main equation. This was our quadratic equation that we had to solve for v. So now let's use the quadratic, solve it using what? The quadratic equation, which is, hey, v is equal to plus or minus b squared. No. Holy Toledo! There's a lot of negatives in here. That's why it's awful. So we have negative b plus or minus the square root b squared. Obviously this is not negative, but we do have a negative 4ac. This one trips me up all the time. All divided by 2a. Our a term is 10. Our b term is negative 30. Our c term is 2.1. And so let's throw this in. So our negative b is going to be 30 plus or minus. B squared is going to be 900. And that's the other thing. This form of the quadratic equation makes your numbers huge. Where we already have the square root of 900. Where over here, look at this. Look at what we had. We had the square root of 2.04. Because we didn't divide by 2a. We didn't divide by, our a term was 10. We didn't divide by 20. You know what I mean? So we don't... Yeah, so that's the other thing. And if this term has to be 20x, but then it has to be that squared. So 20 squared, this term has to be 400 times greater, if I got that right. So that's the other reason why I just don't like the quadratic equation. And it's fun to, not like something. Because, I don't know, sometimes that gets you more views and stuff. Anyway, so now we have 4 times 10 times 2.1. So this is going to be 40 times 2.1. Now, am I doing this right? Yeah, this is positive root, so we do have a negative here. And we're going to have 2.1 times 4 is 48. Is 84. Yeah, no duh. Cool. I don't even know if I got that right. 40 times... Well, I know that 10 times 2.1 is 21. Then times 4, that's going to be 84. Okay, hell yeah. So we have 90 minus 84. Can I do this one? I think that is 820, but it's 816. I had to do that kind of couple steps. So 900 minus 84 is 816. So we have 30 plus or minus the square root of 816. Again, this is why I don't like the quadratic equation this way, divided by 20. And so we have 30 plus the square root of 116 divided by 20, all divided by 20. Yes, this gives us 2.928. That's our answer for our velocity. And then the negative root is going to be 0.0717. And it's just, wait, does this give me a different negative root? Is that possible? I don't think so. So let's see. We're going to do the negative root of this. Negative square root of 2.04 plus 1.5. No, yeah, obviously those negative roots are going to be the same. But yeah, oh, it's 0.07. Yeah, that's close to 0.1. That's what I had in my head. All right, so we get the right answer. This is the speed of Malachi. We did it by deriving the quadratic equation. And let's derive the quadratic equation again. So we're going to have this side is equal to 0. We can do this a lot faster now because we're going to have b over a is equal to negative c divided by a. This is x plus b divided by 2a. I can see if I square this, I'm going to have b squared divided by 4a squared. I'm going to take the square root of this and then subtract b over 2a. So that's how fast I can do it, and this gives me my value for x. And so what do we do to this? Well, we need to multiply by a 4a right here and multiply by the top by 4a. So you already see this is that negative 4ac term. And so now we can, and then we're going to have b squared. I'm going to already move these. So I'm going to have b squared minus 4ac. And we got the denominators the same. This is 4a squared. Denominators are the same, so we can add those. We're still going to have the denominator be 4a squared. And we're going to have the square root of it. But now when we minus b divided by 2a, and again, we're going to use that trick where we can take the top and then take the square root of the bottom. And when we do this, we're going to also use that kind of product rule where we can take the square root of 4, the square root of a squared. Okay, hell yeah. And each of these is going to be 2a. So now this term becomes square root of b squared minus 4ac divided by 2a. I guess I'll write it right here. Square root of b squared minus 4ac divided by 2a. And we still have this term, minus b divided by 2a. And sorry, I'm bad at doing the plus or minus, positive and negative roots on the square root. Okay, but heck yeah. So now, because the denominators are both 2a, and because, yeah, it's really hard to see that this is 2a after you factor it out, but after you go through this process, hell yeah. And now I can just subtract these. And it's just fascinating. See how, like, hey, your negative 4ac was over here when you complete the square, but they just choose to put it over there just by convention. And then once you get down here, you're actually subtracting this term and it's over there. But in the quadratic equation, they bring this term in front. So that's where you get negative b plus or minus the square root of b squared minus 4ac. So they just do two steps that are just farther away from kind of like the intuitive reality of this equation, and obviously it's divided by 4a. Yep. I'm sorry, divided by 2a. All divided by 2a, and so that's x. So hell yeah. So that was deriving the quadratic equation. Always good. Anytime you're going to use the quadratic equation, like I would at least derive it to this form. Like, see how that took like 2 steps, like here to here. You know, just like 3 to 4 steps to get there. This took twice as many steps or more to get to the full quadratic equation. And again, these numbers, because it's like this is just b squared. This is b squared divided by a squared. So this is significantly smaller. And then, you know, when this is, like, let's say this value is 40. That happens a lot, square root of 40. Well, hell, I know that the square root of 36 is 6. Like, what we had was the square root of 816. I have no idea. Like, at this point, you know, because the square root of 1,000 ain't anything cool. You know, like like the square root of 100 is 10. The square root of 10,000 is 100. And so, I don't know, the square root of 400 is 20. And yeah, so I mean, then you get into just factoring this. Well, I could factor out 100. I mean, that's honestly the first thing. Even this is such a good skill to do. Like, hey, I can at least factor out 100. And so let's do that. So this is the same thing as 8.16 times 100. And so then we just use that same thing. Is the square root of 1.86 multiplied by the square root of 100. Oh, no duh. This is just 10 times the square root of approximately 8. Square root of 8 is approximately the square root of 9, so this is pretty close to 30, you know. So hell yeah. So maybe this is 27, and then when we do it, square root of 816, we get 28.56. All right, hell yeah. So I think we've thoroughly demolished problem 3. It involves this equation, which is not obvious that's a quadratic equation. We got it into a quadratic equation, and we just probably spent the last hour just really honing in on the quadratic equation. But also, prior to that, I used a calculator method of just like, hey, just guess, and then refine your guess. Okay, sweet. So now we are going to move on to problem 4. And so this is the last problem. Problem 4. So yeah, we're not moving in the y direction. That's kind of what it says. So Malachi and the group starts at point A, and they walk to the end of the travelator. Malachi is going to be on the travelator. The group's just walking on the ground. Cool. And then they return. So we start at point A and finish at point A. And then and so this says, hey, the group speed is going to be u. So that's going to be the group speed. Malachi's speed is going to be v. This travelator speed is to the left, and it's going to be w. It says you may not assume that u is 1 and that w is 0.7. And so what they don't want you to do is what we have been doing, just like, hey, let's just guess a number. And they don't want you to assume that that's all, I guess. And they don't want you to assume the travelator speed is 0.7. Okay, so the travelator and also doesn't have a length of 20 meters. Its length is s. You know what I mean? So we have all these factors. Malachi walks at a constant speed. So that's the we've done that. Cool. And it says determine the speed of Malachi and the entire group. Let's read this. Determine speed v, Malachi, such that Malachi and the group return at the same time, and give your answer as an algebraic expression. And because we spent so much time on being like, hey, what is Malachi's speed this way? Well, it's going to be whatever speed Malachi chooses. Let's say it's 3. And, you can do this however you want to do it. Like, I would challenge yourself of not using these values, but still use some sort of, like, I don't know. Like, if you can't just do this all in one go, still put values on it. Like, yeah, challenge yourself and don't use their values. So I'm going to say Malachi is walking at a speed of 3 meters per second. The travelator is a speed that way at 2 meters per second. So Malachi is going to have a speed of 1 meter per second. And let's say this is 100 meters. That would make sense, kind of like a football field long type thing. So it's going to take 100 seconds to get down here. 100 seconds. I don't know. If Malachi gets down here in 100 seconds, well, let's see how long it'll take the return trip. Malachi's speed is going to be this 3, plus the travelator speed is going to be 5. So now Malachi has a speed of 5 meters per second this way. So we had 1 meter per second this way. I'm just going to do this for Malachi. And then we got 5. We can travel 5 meters every 1 second. Well, I can see that there's 20 of those in 100 meters. So cool, I can just see that it's going to be 20 seconds. So Malachi's, and how did we get that? Well, you would take 100 meters divided by 5 meters per second. Your units cancel and you get 20 seconds. So Malachi takes 100 seconds to get down and 20 seconds to get back. Now the group has to get down and back. So the group has to travel 200 meters. Okay, sweet. And the group has a speed. So if we have the group and their speed in meters per second, this is going to be the time it takes the group. So, well, it took Malachi 120 seconds. So now we can just maybe solve for the group speed. So the group speed is going to be 200 meters divided by 120 seconds. And that's going to be 200 divided by 120. That's going to be 1.66 meters per second. So hell yeah. So what we just did right here is exactly what we can do for our equation. And, you know, now that I'm realizing it, I should have come back here. So let's do this just kind of as a warm-up, since we have this problem fresh. Is that we put a letter just on Malachi's speed. So let's go back and put a letter on everything. And so this one's going to be kind of different. Well, I don't know. Maybe let's do this. So this whole distance is going to be s. S is going to be 20 meters. You know what I mean? Just so it's kind of similar to our original problem. But in this problem, we have a half of the distance because Malachi kind of started right there. Even right here, this group only has to move half the distance to point A. And so let's go back and say that this was 10 divided by 1. This is the speed of the group. So now let's go put letters on things. So this 10 meters is going to be this total distance s divided by 2. I'm just going to do 1/2 s divided by, this is Malachi's speed. The travelator is w. And it's in this direction. So this is where, yep, you know what I mean? Do you put negative w and say that the travelator speed is a absolute positive number? I don't know. I think I would for this. I would just say, hey, the travelator speed is just an absolute value. So I would say Malachi minus w plus 20 is just s divided by Malachi's speed minus, no, now this is plus the travelator speed. Cool. And this is going to be equal to 1/2 s divided by the group speed u. So there is the equation for this. We just knew just pretty much everything about it. So now we can go back to this problem, and we can kind of see what we can do. All right, sorry about that. Let's see if I can just write in here. Okay, so all right, first up, what did we do for Malachi? So maybe we should just do this problem again. And yeah, we got more space to work with. So we said Malachi's speed was going to be 3 meters per second. And yeah, let's put right now, let's put a label on that v. The travelator speed is going to be, what did we say that was? That was going to be 2 meters per second. Cool. The group speed, after we solved that was going to be 1.6 meters per second. That's going to be in that direction. Well, I guess both the group and Malachi are going to walk to point A and then turn around and then walk back. And then this distance is 100 meters. So we got the time for Malachi to get here. That was going to be his speed of 3 meters per second minus 2 meters per second. And that was going to give me 1 meter per second. Then we took this and we needed to know that we went 100 meters. So then we took 100 meters divided by 1 meters per second, and that was going to be 100 seconds. And then on the return trip, we said this 3 meters per second plus the travelator speed. You know, so these are just all intuitive things that you can do, and then you can go back and see, like, well, what did we do to get an equation? So now we have a faster speed of 5 meters per second. We're still going 100 meters to get back to point A. So we're going to have 100 meters divided by 5 meters per second. That's going to be 20 seconds. So then we're going to add these two things up, and we're going to get 120 seconds. Okay, and we know that the whole problem statement says the group has to get here at the same time, and the group is traveling at a constant speed. So, and that kind of goes back to that original equation of what's the definition of velocity? It's change in position, change in time. And as long as this is a constant or relative, and in this case it's constant. So this is an equation of 3 different things. I could find the change in time for the group. I know that they have to have, we know that they're going to take the same time as Malachi. So what I want to find is this velocity of the group. So U of the group is going to be the change in position, change in time, and I can see that that's going to be a total distance of 200 meters, and it has to be this 120 seconds. So then we get 1.6 meters per second for the group. Cool. And then we kind of work backwards to get the speed of the group. But now we want to know if this is the speed of the group, let's work forward. Let's say that was just given. The speed of the group is 1.6 meters per second this way. They're walking along the ground. How long is it going to take to walk to point B to point A? So again, we have this equation. We know the velocity. We don't know the time, but we do know that they have to do 200. So let's solve for change in time. Change in time is going to be change in position, velocity. And this is the kind of the equation we've been using all today, and it's the one that's a little bit trickier. It's the, I like to say, use the units or the equation, because this is in meters, this is in meters per second, and units cancel and seconds pops upstairs. And I just double down on this one because it's not so intuitive, and it's going to be useful for me to always use this type of analogy, or this, units are the equation when doing like, electromagnetism or current. Definitely there's so many equations on current that I'm not, very strong, and I actually don't, I can't even tell you one equation that I would know. Kind of just a general sense of voltage, resistance, and ampere. I don't even know if I'm even saying that right. But anyway, but yeah, this process would be very helpful. Okay, so let's solve for that change in time. So we have 200 meters divided by 1.6 meters per second. So we got I'm going to store that as alpha u. So 200 divided by alpha u. So we get 120 seconds, and that's a check on reality. So those two times are the same. So this is the part of the equation where we're going to have one side of the equation is equal to the other side. So there it is. So this is this side of the equation is equal to that side. You know what I mean? And spell it out right there. 120 is equal to 120. So now we can build our equation. Even going back to like, well, how did we get these two things? We're going to add two things over here, and we're going to add 100 divided by this 1. But how to get this 1 was 100 divided by 3 meters per second divided by 2. So I'm just going to kind of write that here, and then we'll put in the letters. So this time is going to be 100 meters divided by 3 meters per second minus 2 meters per second. Now we're going to add, this is another 100 meters, but now we're moving faster. 3 meters per second plus 2 meters per second. And it's just fascinating, especially when you write it in a different form. Still kind of mentally like have an idea of where these things came from. You know what I mean? I mean, you just did them like line item on your paper, and then you went back and added them together, or I'm just saying colloquially I did. But then when you write it here, just know that it's in a stranger form, but still it's exactly what we did. So we cool. We just did this first. That's kind of the tricky thing, is we took that distance and then divided it by something we did first. So cool, we have those two time frames, and that's going to be equal to this. This distance is going to be 200 meters divided by the speed of the group. Now the speed of the group, is just going to be a parameter that's given. So that's just 1.66 meters per second. Cool, so now we have the equation, and now we can actually write this as an equation. So we're saying this distance is s. This will probably be a good thing. Go back to your paper and be like, okay, this distance, this variable is u, speed is w, this speed of Malachi is v, this 100 is s again. So yeah, we're pretty much set. This 200 though is 2s. All right, let's do it. So we have s divided by v minus the speed of the travelator plus the total, the 100 meters, the s divided by v plus w, this Malachi speed plus the speed of the travelator, is equal to 2s divided by the speed of the group. And that's it. That's the algebraic expression. And if you get better at this, you can just be like, okay, the time of the group has to equal the time of Malachi. And I know those times have to be the same. How I get time is distance divided by velocity. And so I could be like, well, on the path, it's going to be the distance s divided by Malachi's speed minus the travelator plus, on the way back, that distance divided by Malachi's speed plus the travelator. And then that's got to equal, that time has to equal the group speed, which is, the group speed is just two times the distance, traveling at the same speed, divided by their speed. All right, booyah. So that's that. And now we're going to use that to answer some questions about this, this problem. So we have this equation, s divided by Malachi's speed minus the travelator plus the distance back Malachi's speed plus the travelator is equal to, that time is going to be equal, you know, the group has to go 2 times that distance and the group has a constant speed. So it's always good to talk through an equation as well. All right, hell yeah. So now we're going to answer these questions and be done. And these questions, I don't know, they're not super simple. All right, booyah. So the first question, it says, explain what happens to Malachi's speed, to v, when the group speed is very large. Okay, so since this problem already stated that you got the algebraic expression, this is where, you know, you can just start playing around with things, especially since you have ratios. You know, if a denominator, it says if u is very large, well, if this u gets huge, I don't know, this term goes to 0. Is that what we want to do? I kind of forget. Explain what happens to v when u is very large. Oh, okay. So the things that we can change, the travelator speed is constant. This distance is constant. So that's the other thing. For this algebraic expression and for what they just asked, you know what I mean? They're trying to compare u and v. Only those two variables. So with a set distance and a set speed of the travelator, those two things are constants. But when we take this to be like infinity, I mean, this is going to be some number divided by a hell of a big number. So that's this is kind of the things that I use, is like just draw, you know, this expression. And so this is basically going to be 0. And so the only way to get this 0, because we have this distance, that doesn't change. And this doesn't change. And then even though we're just also adding it to, you know, this side of the equation, but this v has to get huge. So there you go. And then that's only kind of the first part of it. Like so cool. Like if this gets huge and becomes 0, these two things also have to add up to 0. But the only way that's going to happen also is if I don't know if that was what they're trying to say is all right, hell yeah, got a new battery in. And then I just kind of read the problem, because in the first part of this problem, they wanted an expression in terms of velocity. So where we're heading with this is we have to actually solve for velocity. So we're going to run through that whole process of making the denominators the same, getting all the variables to one side, seeing that we're going to have a quadratic equation, and then we'll complete the square. So at the end, we'll get an equation for velocity in terms of all these other variables, and then we can ask these questions just way more simply. But yeah, it's kind of fascinating. Let's like when they say the travelators. Explain what happens to v. So if the group goes really fast, like the travelator doesn't, like the travelator gives Malachi an advantage on the way back. That's you know, kind of where that squared term comes in. But as long as the group goes really fast back and forth, that advantage to Malachi isn't as much. And so Malachi's speed will be matching the group. So that kind of whatever Malachi had, like the group will get here first because the travelator's moving that way. But then on the way back, the advantage won't be that much. It'll almost be kind of probably a linear part of the curve or whatever. But that's kind of what that's saying. If the group goes hella fast, Malachi's speed kind of just has to match, even though he will lag on the way there and then speed up on the way back. That's where that is. Okay, so let's... yeah, and it's just kind of fascinating because you really can't tell too much. I mean, you're going to have, you can make this really big. You're going to have 0. These would have to be really big as well. So that was close enough where if the group speed is really large, Malachi's speed also has to be very large and then has to be equal. So if the group speed is really large, Malachi's speed basically has to match the group speed. And then the other question was, what happens when the travelator's speed is really large? Well, if the travelator's speed is really large... oh yeah, this is kind of fascinating. These essentially become, like something divided by a really large number is 0, and so what happens to, what does it say? What happens to I should just read this. Explain what happens to V when U is very large compared to the travelator. Did that. And what happens when W, the travelator, is very large compared to the group speed. Oh yeah, so if this is really large... oh, this is fascinating. Alright, hell yeah, and I forgot that this is negative, so when this becomes really large, this is going to be a, but Malachi's speed always has to be bigger. See, that's the thing, is like, Malachi's speed has to be bigger than the travelator, because if Malachi's speed isn't larger than the travelator, he can't even move this way. So if the travelator's speed is, oh, this is what happens, so yeah, just in general, if the travelator's speed is like, so the group speed is just going to go back down in normal pace. Let's say it takes them 20 seconds to do that. Cool. If the travelator is just whooping, and if Malachi just hopped on the travelator and didn't walk at all, maybe it takes him 1 second to do this. So what this means is if the travelator speed is really high, Malachi has to move basically the same speed as the travelator, just a little bit faster, to make sure that he uses all 19 seconds to get to this end, and then that last second to get all the way back. So that's basically what that means. And we just did it with a scenario where the group took 20 seconds. 19 of that might have been used for Malachi to get to here. You could say the group takes 1,000, or let's just say 100 seconds, and let's say within 1 second, Malachi is going to go that distance because the travelator is hella fast. Well, Malachi has to spend 99 seconds to getting to this point, and then that last second. So Malachi basically has to travel at the speed of the travelator, just a little bit higher. But those two things, Malachi must move faster than the travelator for him to actually physically get to this point, and the Malachi's speed will pretty much match. V will pretty much match W when the travelator is really high. So that we can definitely see that from that scenario. Okay, so let's go through the whole process of running through this algebraic expression, because we actually didn't. This problem said determine the speed of Malachi and the group. Give your answer as an algebraic expression. So we want to solve just for that Malachi speed. So let's do this. So we have this equation. We're going to get the denominators the same. So we're going to have S, V minus W. We need V plus W. And then we get to put a V plus W upstairs. All right, over here we have V plus W. We need a V minus W. And then we'll put a V minus W upstairs. All right, so these two terms are 1. and they don't change the algebraic expression at all. This side we'll just leave the same for now. And now we can FOIL this through. We can say that this is, I'm going to do the bottom first, v squared plus VW, but then we'll have minus VW, and then we're going to have negative W times W. So we're going to have minus W squared. That's going to be downstairs. Upstairs, we're going to have SV plus SW. Over here, we're going to have that same thing downstairs. And now we're going to have SV minus SW. But even right here, your mind goes blank, whereas just these things are meaningless anymore. And even when they had numbers, I could at least follow the numbers. But it's a little trickier following the letters. We can still see, I can maybe make the V's a little bit darker, just to know that that's kind of the variable that we're trying to solve for. Okay, and that's going to be equal to SU. I'm going to come over here. Since the denominators are the same, we can now add these terms. So we're going to have SV plus SW plus SV minus SW divided by V squared minus W squared is equal to 2SU. What do we have? We have SW minus SW. Cool. So those terms cancel, and we're going to have 2SV. Hell yeah. And now we're going to take this upstairs. Might as well just do that in a few steps and take our time. So we're going to have this. I'm going to put that first. V squared minus W squared. We're bringing it up. It's a multiplication. So we have 2S divided by U. I got to FOIL this through. So we're still going to have that 2SV on this side. And we're going to have 2S V squared divided by U. And I kind of know that my V's terms are kind of what I'm going to do the quadratic equation on. So I'm just going to kind of put this term last. So when I FOIL this, that's what I did. Alright, now we're going to have a minus 2SW squared divided by U. Okay, sweet. Now let's get, now this doesn't have any W term. No, this does not have any V term. Sorry if I'm calling it W. We need to get this V term over there. So I'm going to say 0 is equal to 2S V squared divided by U minus 2S V minus 2SW squared divided by U. See, yeah, I mean, if you didn't do this with numbers, and even doing it with the letters of the quadratic equation is hard enough. But now we actually have, I mean, for our A term is 2SU. Our B term is negative 2S. And our C term is negative 2SW squared U. Yeah, so it's pretty wild. But what we're going to do is we're going to complete the square. So let's grab a fresh sheet of paper. So we're going to have, I'm going to write this way. 2SV squared U minus 2SV divided by, whoa. Sorry, there's no other term there. Minus 2SW squared divided by U. Alright, this is equal to 0. So I'm going to use that same process of completing the square. I'm going to get this term over. I'm going to do, well, I need to isolate this V squared. So let's do that first. So I'm going to have V squared minus, so maybe good to, so this is negative 2S, and now I want to divide by 2S divided by U. Okay, the 2S's cancel, the U pops upstairs, so this just becomes negative U. Okay, that was pretty sweet. So we have negative UV. Cool. This term I got to divide by 2SU. Oh, now I can just see I have a 2SU. I'm going to divide by 2SU. Sweet. So this term just becomes negative W squared. Hell yeah. And I mean, I think you can see that. 2SU divided by 2SU, that becomes 1. We still have this W squared, still a negative. I'm going to get it to the other side though. I'm going to do that all in one step on this one. Cool. So now that's to the other side. Now I'm going to complete the square. This is going to be V minus, still got to keep that minus, but it's going to be U divided by 2 squared. And now I can just say, hey, when I do the square root of this, I'm going to have V squared. I'm going to have V times this, V times negative 1/2 U. It's going to be a negative, so yeah. And then double it. That's going to be my negative UV. So I already see that. The term I'm going to pick up is this squared. So that's going to be U squared divided by 4. So that's what I'm going to pick up. I'm going to add it to this side, add it to that side. Because this term is a square term, it's always going to be positive, so that's cool. You can just always add it over there as a positive. Okay, now I'm going to take the square root of both sides. Make sure to get the positive and negative square root. That just indicates that you understand that there is two solutions here when you do a square root. One's positive, one's negative. Both can be a tangible, but in this case, probably only one is a real solution. That's where I need to watch more videos on imaginary solutions, or solutions that are, like what's the geometric, like what does it, giving another solution that doesn't have a tangible meaning, like what does that mean? Anyway, all right, so then when we take the square root, we're just left with V minus U squared. So we can just say V is equal to this plus U squared. Okay, hell yeah. So now that wasn't too bad. So after, doing the quadratic equation, doing this form, completing the square from this form, we skipped a lot of steps. We didn't skip a lot of steps. We can just do 2 steps at once, and you can see that we can get there fairly quickly. And this is such a cool form. You don't have to divide by 2a at all. We just have the square root term and then plus one other term. So now we can ask those questions just way easier. What happens to V when U is very large? Okay, sweet. So when U is very large, this is so easy now. And I'm glad we went over it the other way, because it was better just to do it from an intuitive stance, and we can do that again. What happens to Malachi's speed when the group is just hella fast? Like Malachi's speed basically has to match the group speed. We saw that from intuitive sense, and maybe we didn't understand why it was. Maybe we weren't honest with ourselves of saying that that wasn't accurate. But when we come over here, when we see U is like hell, we're talking hella large. We're talking U is so large that the travelator speed is just like worthless. You can just imagine the travelator's not working. And like that's the other way. When U is large, you can just imagine the travelator is just hardly moving at all. And so the group in Malachi basically have to walk at the same speed. It's like the travelator. That's what we're talking about when things are getting like hella large. Like it only takes a couple factors of 10 for this travelator to be like not moving. If it has a speed of 1 meter per second, cool, that's a little advantage, or that's definitely useful. But if it slows to 0.1 meter per second, maybe it's broken. And if it's 0.01 meters per second, is like maybe you can't even tell it's moving. You know what I mean? And again, another factor of 10.001 meter per second. And what is this? This is 10 centimeters. This is 1 centimeter. And this is 1 millimeter. Could you even tell that the travelator is moving 1 millimeter a second? I don't think so. So it doesn't take too much of a factor of 10 to make that travelator just totally. And I think that aspect is people don't think about. And this is where I can double down. Especially when you have like integration. When you're like, hey, let's take a smaller and smaller slice until it's an infinitely small slice. It's like, forget all that. Just take a small slice where it like doesn't matter anymore. Where there's a small enough slice that's still visible of your graph where like your answer is still accurate within 3 decimal places. That doesn't take much. You know what I mean? And that's very far away from an infinitesimal slice. You know what I mean? Where you get an answer that would be, you know, even 100 digits. An answer accurate to 100 digits isn't even that small of a slice compared to negative infinity. You know, compared to so small it's approaching 1 divided by infinity. Anyway, so yeah, we can use that. So that's a better way to do it, just from an intuitive standpoint. But from our equation, yeah, this is so large that this addition to the travelator speed, we already said, yeah, 0.0001 squared. I mean, this is just nothing. And then, so when we get nothing there, we get the square root of u squared 4. We can use all those tricks that we used today. We got the square root of u squared divided by the square root of 4. This just becomes u divided by 2 plus u divided by 2, which is just u. And we can see that v is equal to u. So that's the mathematical expression that you get, you know what I mean, once you do that. So that was the first one. Explain what happens to Malachi's speed when u is very large compared to the travelator, and we just said it in the opposite way. When the travelator appears to be not working, but it's just moving at a molecular pace, yeah, Malachi's speed has to match the group speed if they're going to meet at Cinnabon at the same time. Anyway, so what happens to v? No, we'll do the next one. I'm sorry, I'm horrible at reading. I'll try to get better. We did this. Explain what happens to v, Malachi's speed, when the group speed is very large compared to the travelator. But this is also good. Like when you're reading out variables, like try to read it out of what they are and not just what they, you know what I mean? There's so many times where physicists will just be like, all right, this thing's spinning around this point and it has an omega. You know what I mean? It has an angular speed. You know what I mean? It has, you know, like even though angular speed is hard to say, there's so many professors that will just call it an omega, like that's supposed to mean anything. Anyway, you know, just like you would say it has a velocity v or it has a velocity u, you would say this has an angular speed omega. You know what I mean? So all right, let's keep reading. And then what happens when the travelator is very large compared to the group speed? So sweet, and we weren't quite sure about this one, but the travelator is just hella going hella fast. Well, yeah, it was. We already did this one, and let's tackle it again. Let's say the travelator is moving so fast that it takes a blink of an eye to get Malachi back here, which is still not that fast. In relatives of how fast things can move, like the speed of light, like within a blink, within a click, Malachi is you know, from point B to point A. So when the group takes 100 seconds, 50 seconds this way, 50 seconds back to get to point A, Malachi basically has to use all that 100 seconds to get to point B, and then instantly is back at point A. And not even instantly, it's just actually that took some time and matches the group. So Malachi basically, in that situation, has to travel at the speed of the travel. That is the most bizarre thing, because if Malachi is right here and moving at the speed of the travelator, Malachi will always be right there. But for Malachi to actually start moving this way, Malachi's speed will always have to be just larger than the travelator. But if we're talking just barely more than the travelator, you know, Malachi will have this relative speed during that 100 seconds that will be going in that direction. So hopefully I'm saying that right, and I kind of want to derive like what that speed would be or whatever, but I think we did it. So now let's go to our equation and try to do it from our equation. What happens when W is very large compared to U? And we've already made the assumption that, yeah, we're talking orders of magnitude larger. And I've done a video where, hell yeah, when you have something like 4 times 10 to the 8 squared plus 4 times 10 to the 8 like this, it doesn't even compute. This is going to be 16 with 16 zeros. So let's write that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Always, even if it seems ridiculous, write them out. And this is going to be 4 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So if we added these, we would add a 4 right here. So that would be the number. 16, a bunch of zeros, a 4, and a bunch of zeros. And so, well, and if you're just interested in 3 decimal places, like this is absolutely meaningless. You know, like when using this number, you would just write 16 times 10 to the 16. So that's what this would be. So that's what we mean by when one is large, the other one, the addition of the other one is essentially adding 0. Cool. So if omega is hella large and u is tiny, even when we get here, we're going to have omega squared square root that, and then we'll just have omega. But again, we're omega plus u divided by 2, and we're saying that omega is way bigger than u squared. You know what I mean? So this term just drops out. And we'll have Malachi's speed is equal to the speed of the travelator. So that's what happens when the travelator's speed gets really large. You'll have Malachi's speed is equal to the travelator. But let's refine that one, because there's sometimes the in-between places where you're just like, yeah, the travelator's speed is hella, and we're squaring that. So now, then we get this scenario where we have 4 times 10 to the 8 squared plus, and then plus a smaller number squared is still going to be 0. So you definitely are going to get the omega. We're going to get omega squared square root that. That's going to be omega. But let's say the group speed it's not insignificant, but this term becomes insignificant. This term becomes more insignificant than this term, but we still might have, and I'm calling this omega. W plus u divided by 2 is equal to Malachi's speed. And so we could get this term over there. So we could say the travelator's speed is... yeah, so there you go. I mean, there would be your equation. Malachi's speed would be the travelator's speed plus half the group speed. I think this is closer. Yeah, and let's run a scenario where the travelator's speed is 100 and the group speed is 1. And then so what I'm saying is that Malachi's speed will be 100 plus 0.5. 100 plus 0.5, and Malachi's speed will be 100.5. And let's see if that works using what we just did. So we're going to have 100 squared. No, we're basically saying this term is going to drop out, and let's see if it does. So we have 1 squared divided by 4. And so we would have 100 squared. So this would be 10,000 plus 0.25. So that's what I'm talking about. When you have something squared plus something smaller squared, it's very insignificant, because the square root of 10,000 is 100, and the square root of 10,000 plus 0.25 is basically 100 again. So it's 100 plus 0.00125, when we were saying Malachi's speed should be 100.5. So sweet. So because we still have the group speed of 1 divided by 2, which is 0.5. So we have 100.00125 plus 0.5. So this term is more significant. It also doesn't become just 0 like I said. Like at very high speed, sure, Malachi's speed it seems to be equal to the travelator, but we know from practice that Malachi's speed has to be slightly faster. And so this term still will apply, and you get this. Malachi's speed has to be the travelator's speed plus 1/2 the group speed. And this term, like this analysis I didn't pick up on the first go doing this. So yeah, so this was pretty satisfying. And I'm just glad there's a lot of, I mean, I could have not seen to do the quadratic equation and get Malachi's speed just in terms of the other variables. And just, you know, just get down to something like this and try to make some assumptions. But, so booyah. So we did it. Did we get our 7 marks for this one? Hell yeah. You were supposed to have 15 minutes on this. And so with these, I don't know like how you would actually, they're tests, so if you haven't done these problems, like I don't know, there is, I guess, like there's an idea of like, oh, I've done similar problems, and yes, I've done the math, and I get how like when you analyze the math, I've done other problems where you get an equation and said when one gets really large, what does the other one do? And so, you know, all of those skills could have been you know, gotten from doing other problems. But yeah, this was kind of fascinating. So yeah, I think I'm done with this one. Thanks for joining me, and guess what? That's a video.